So how do we actually evaluate a double integral? The Riemann sum definition of a double integral will not be easy to use. In fact, it will be nearly impossible in most situations of practical interest. And unfortunately, there is no fundamental theorem of calculus that applies for a double integral. However, it will turn out we will just use single variable integrals. So what we're going to do is try to motivate this by talking about the volume problem again and going back to a technique you've learned about in calculus called volume by the slicing method. So remember that if you've got a function that's positive and you would like to figure out the area underneath that function between two values, you simply calculate this definite integral. If we've got some function that now lives in R3, and we would like to calculate the volume underneath such a function, so let's say it's got its usual three-dimensional axes like this, what we're going to do is cut this volume up into slices. So let's take one of these slices to live somewhere here. That slice is being held at a fixed location, x, at this value here on the x-axis. So our function is up here, f of x and y, and we're going to assume that it's positive for the purpose of this motivation. So the area of that slice is simply an integral from c to d of our function, f of x and y, and we're integrating over that direction. Now, just like before, the rectangle is defined by this Cartesian product. What this produces is an area of that blue face that's a function of the value x. So depending on where you held this slice fixed in the x direction, you're going to get a different value. So this is what's called partial integration. Now you can compare this with partial differentiation, where we hold one of the variables fixed and then we differentiate with respect to the other. When we have a partial integration, we hold one of the variables fixed and integrate with respect to the other. And so now the volume is simply given by integrating over all of these x slices. So what ends up happening is that we substitute this expression inside here. This ends up being what's called an iterated integral. Iterated means we have to perform the integration one at a time. We always start with the inner integral first, and this is a function of x, and that means then that the second integral happens here, and these letters need to match. Once you start with the inner integral, it's going to get rid of, in this particular case, all of the y values. You'll be left with x's only, and then the second integral will simply be an integral with respect to all the x values. Now, the other thing that we will notice is that volume should be the same if we reverse this order. So, for example, if I had this three-dimensional solid again, and I decided to take slices held fixed at some y value, then the area of one of these slices would now depend on the y, and I would integrate through all the different x values. The volume then would be an integral over all those slices in the y direction. So we suspect that regardless of the order that we integrate things in, we will get the same volume for this function, regardless of which one is the inner integral or the outer integral. Now, just to try to show you how the technique of iterated integrals works and how partial integration works, and to try to see if our suspicion is correct, let's take a look at a simple example. Now, in this particular case, we're going to take a rectangle that's defined like this. Here are our x values and here are our y values. Now, we're going to try this in both ways. So first, let's compute the integral with respect to y, and then second, compute it with respect to x. So we'll have an integral from 0 to 1, x squared plus y, dy first, and then dx second. Now, in this particular case, y is the integration variable, so anything with an x is considered to be a constant. The outer integral remains the same, and we'll just be performing a basic definite integral here. X squared is a constant, so its antiderivative is x squared y plus y squared over 2. This is going to be evaluated from 0 to 1. We'll now have an x squared times a 1 plus 1 squared over 2. Subtract, x squared times 0 plus 0 squared over 2. The first, or the inner integration in this particular case, gets rid of all the occurrences of the letter y. We should be left with something that's a function of x, and that has to match the second integration variable. Now we just perform a simple integration with respect to x. So we'll get x cubed over 3 plus x over 2, and this has to be evaluated from -1 to 1. So this is going to give us a 1 cubed over 3 plus 1 over 2, subtract a -1 cubed over 3 plus a -1 over 2. So I'll get a 1/3 plus a half, subtract a -1/3 minus a half. This will give me 2/3 plus 1, which is 5/3. So we'll try it now in the second direction. So we will take the integral from x to be first, and we have our function x squared plus y will go dx, and then dy will be second. With respect to this inner integral, this is a constant. We'll get an x cubed over 3 plus xy, evaluated from -1 to +1, and then the result is essentially getting rid of all the x values. So we'll have a 1 cubed over 3 plus 1 times y, subtract a -1/3 over 3 minus 1 times y. Simple integration, we'll get a 1/3 plus y, subtract -1/3 minus y. This is going to give us an integral of 2/3 plus 2y, and just like we expect, we've removed all the x dependency by integration. We should have only a function of y, which we do. We're going to integrate that with respect to y. We'll get a 2/3 y plus y squared, 2y squared over 2. From 0 to 1, those will go away. We'll get a 2/3 plus a 1, which is 5/3, as we expected. We get the same result. Now, this is just a suspicion. It's not a proof. We would love to know when exactly this will be true. Is this a coincidence? No. This result is something called Fubini's theorem. And Fubini's theorem says that if f is continuous on the rectangle R from A to B, Cartesian product with C to D, or f is piecewise continuous, then we know that f is integrable, and it will turn out that the double integral can be calculated as an iterated integral, and moreover, the order in which you calculate this iterated integral is irrelevant. You can decide to calculate with respect to x first or with respect to y first. While the result may be the same regardless of the order in which you do it, the practical matter of actually calculating it may not. It might not be the same in terms of difficulty level for you to do x's first versus y. It all depends on the problem. What I'm going to do is prove this for you for the simple case where the function is continuous on R. Now we're going to let R have the following partitions. The x values partitioned x0, x1, x2, all the way up to xn, where xi is just a plus I delta x, and delta x is going to be equally spaced here. We're also going to let y be partitioned with the exact same number of points, though generally it won't really matter. I'm just trying to illustrate this to you for a simple case. So this would be c plus j delta y, where delta y is now d minus c over n. And the point here is that we know that the function is continuous on R, so that means its integral exists. And if the integral exists, that means this limit has to exist. This is the limit of a double Riemann sum, where I've got some f of xi star, yj star, times some area element delta a. And I know that this will exist. So my goal is going to be to try to construct this contribution in terms of an iterated integral. So we're going to define this function here, capital F of x, as the function of x that we get when we perform a partial integration with respect to y. Now note, because f is continuous on R, this integral will exist, and that means that this function capital F exists. Now what we're going to do is break up the interval by using the subintervals in the y partition. Now to try to show that to you, I'm just going to take a mock-up here of the y-axis. There'll be y0, y1, y2, all the way down. This integral here begins at c, and so what we'll say is that this function capital F of x is going to be an integral from y0 to y1 plus an integral from y1 to y2, and this will go all the way down from yn minus 1 to d. I'll be able to write this as a sum where j equals 1 to n of an integral of yj minus 1, yj, f of x and y dy. So this is one way for me to represent this particular function. Now I have to take a little bit of a sidetrack here. There's something called the mean value theorem. If I have a function g that's continuous and differentiable, the mean value theorem says the following. There exists some number c between a and b so that the derivative of this function is equal to this particular difference. Or I could take this difference and simply say that it's equal to this. This right here you can recognize as an integral of this particular function. This right here, by the definition of an antiderivative, is simply the function there. So this is what's called the mean value theorem for integrals. I am going to recast this particular integral using the mean value theorem for integrals. And so what ends up happening is that my function f of x is now a sum j equals 1 to n, and I'm now going to have the function f, because it's an integral with respect to y, this is going to be at sum yj star, that's a function of x, delta y. Because here my subinterval goes from yj I minus 1 to yj, and then this yj star, which depends on x, lives between those two values with round brackets. Where am I going with all of this? So now consider whether this particular function is integrable. Does its single variable integral exist? So that means I'm going to form the limit as n goes to infinity of I equals 1 to n of this thing, f of sum xi star delta x. And what I'm going to do is use the x partition here. And in the x partition, I've got an x0 and an x1 and an x2 and so on and so forth. By my result from above, what this is going to give me is a limit. As n goes to infinity, I'll have I equals 1 to n. I'll now be able to put this other summation in j equals 1 to n. I'll have an f of xi star, y of j, a function of xi star, a delta y, and now I'll have a delta x. I want to know if this limit exists. Well, rewrite this. This thing right here that I just calculated, I'm trying to see if this definite integral exists. And what I've just found is that this is the limit of this double summation, where I've got an f of sum xi star, sum yj star, and I've got this delta a. Well, I know that this exists, and it equals the double integral. So if this exists on the right-hand side, this also exists. My integral of this thing f of x dx has to be equal to this double integral, but just a moment ago, I defined that function capital F of x to be the partial integration of this function right here. And so what that means is if I want to calculate a double integral, I can do it with this iterated integrals here. Now, I could also repeat this argument for f of y. That was a partial integration with respect to x. And this would give me that the exact same thing would hold, that the double integral would simply be an iterated integral in the other direction. So what I've done here is proven Fubini's theorem for the simple case of continuous function. There is a proof for piecewise continuous, but it's not as straightforward. Regardless, our intuition is verified.